So another type of motion that we need to talk about is what's called uniform circular motion. Um, we talked about kinematics. We talked about kinematics being a one-dimensional motion. You can talk about two-dimensional kinematics. You can bring it into three-dimensional kinematics, which is talking about motion this way, motion in the z direction. Okay. We also talk about simple harmonic. Now, AP we didn't talk about simple harmonic. It's not part of the required curriculum, but IB we did. So, excuse me. Simple harmonic motion is nothing more than motion that vibrates back and forth along the x-axis. Uniform circular motion is simple harmonic motion in two dimensions. Okay, and it's simple harmonic motion in two dimensions in a specific way. As a matter of fact, if you think about it, it's simple harmonic motion where the frequency of one in the x direction and the frequency of the other in the y direction are identical, and that there's a phase shift of 90 degrees between the two of them. I do believe it's 90. Yeah, because it starts at 0 and 1. Okay, and it can go this way or this way. But it's basically perfect circular motion. Orbital motion, if you will. The moon orbiting the Earth, even though it isn't quite circular, it's pretty close. Same with the Earth's motion around the sun. It's not perfectly circular, but it is really, really close. I mean, there's very little, there's a very small ellipse, if you will, if you're considering the orbital motion of any of the terrestrial planet, or any of the terrestrial, and most of the Jovian. You can tend to believe that they're all relatively circular motion. Now, what defines circular motion is this. You take an object, and you move it in a circular path. Okay? It's totally circular. Now, I didn't do a very good job drawing that circle, but imagine that it is a circle. Now, uniform circular motion says this, that the velocity of that object is either in this direction or in that direction at this point. Okay? So, it's tangential is what we call it. If you expressed it here, it would never intersect that circle. It would basically bounce off that circle at that one point. Okay? So either the velocity of the object is in this direction or it's in this direction. Okay? It's tangential at that point. As you move on to this point, here's my tangential motion. Move on to this point, here's my tangential motion. On and on and on and on and on. Okay? So the velocity is what we call tangential. It's always just nicking that circle at that one point. Okay? The other component of uniform circular motion is that there's a force that's always pointing towards the center. Okay? There's always a pull on that object towards the center of that circle. Cool? And if there's a force doing that, more than likely there's an acceleration. And there is actually what we call centripetal acceleration, center pointing acceleration. Okay? So the diagram, if you were to talk about this point and only the velocity, not concentrating about this orbital motion, the diagram that I want you guys to get out of this is that the velocity at that point is in this direction, or in this direction, if you will. It really doesn't matter. Okay? And the acceleration is always pointing towards the center. And then there's a force that's pointing in the same direction. Okay? That's the kind of diagram that I want you to have. And now you can imagine that the circle, the orbital path is something like this. Okay? So at one given point, that's what you get. Now, some of the properties of it, some of the mathematical properties of orbital motion, of uniform circular motion, is that, first of all, no work is done. If you look at this system and you talk about work, and remember work is that force and that displacement, you're doing positive work if that force and displacement are in the same direction. You're doing negative work, you're slowing the object down if they're in the opposite direction, or at least attempting to slow the object down. They're in the opposite direction, but this, or here's my motion, here's my force, or here's my displacement, here's my force, no work. Because of that, if you were to look at that velocity, you can imagine it moving in this direction. The force is always going to be perpendicular to it. And because the acceleration and force is always center pointing, if I were to move it at this point instead of this point, like so, here's my velocity. Now, mind you, we can pretend that the object is moving in this direction. Okay? It may be easier to see it that way. So it's moving this way. The force is still center pointing. It's still perpendicular. That's what makes it uniform circular. That force is always perpendicular to the motion. Now, in elliptical motion, it's not necessarily that way. As a matter of fact, if you look at motion that's really elliptical, here's my object, here's my force, here's my velocity, they are not perpendicular to it. If I were to imagine displacement this way, I have a small component of my force this way, and I'm slowing that object down. Elliptical motion doesn't behave like uniform circular motion. Doesn't have the same properties. Okay? So, by definition, that velocity is in this direction. The force is perpendicular, center pointing. The acceleration is center pointing. Okay? And there's no work done. Which means that that velocity, that orbital speed, if you will, never ever changes. It stays constant. Okay? Cool? Now, equation-wise, we say that the centripetal acceleration, okay, this is the type of acceleration, that center-pointing acceleration, if you will, is equal to the velocity squared, this component times itself, divided by the radius. Okay? So centripetal acceleration is velocity squared divided by radius. It's this value squared divided by the radius. Whatever that radial value is for that circle. Okay? Cool? Now we can take it one step further and use this talk about it as rotational motion. And instead of v, we talk about omega, rotational velocity, and you end up with r omega squared. Okay? So all of these are equal to each other. Centripetal acceleration is v squared over r, velocity squared over radius, or radius times omega squared. Okay? These are all the same. Got it? Now, if I wanted to talk about centripetal force, and we got to be careful about this. Tension is a force. Gravity is a force. Electrostatics are forces. Magnetostatics are forces. Centripetal force is not a force. It's the result of a force. Okay? And because of that, because it's a result of the force, we look at Newton's second law and we say the sum of the forces, those tensions, the centripetal are, because of Newton's second law, we say the sum of the forces, which are items like tension, gravitational, electrostatic, magnetostatics, all of those are types of forces. Those are the forces we sum up, is equal to ma. Okay, the inertia times the acceleration. When we talk about centripetal force, we're talking about, the sum of the forces equals mass times, centripetal acceleration. So when we look at this, we go, the centripetal force is a result of all my other forces, so that's this. Mass times acceleration. Now, the acceleration was centripetal, so I'm going to just drop that in there. It's not a force. It's the result of a force, or forces. Okay, that's centripetal force. And I can do mv squared over r, and I can go mr omega squared. Okay? Those are all centripetal forces. Got it? That's centripetal acceleration. That's the principle behind it.